Hi, my name is Archie Parcharchi, and my project is titled Seeing Stress Where Crops Show It, Early Detection of Crop Stress via Satellite-Derived Spatial Heterogeneity Collapse. The research question we're going to be trying to answer is, can intra-field spatial heterogeneity in satellite vegetation indices predict crop stress months before harvest time yield loss? In the 2012 US drought, losses exceeded $30 billion. Monitoring systems warned only about 6 weeks before harvest, which is far too late. And my question is, were satellites already showing an earlier signal? Traditional systems track mean NDVI. By the time the mean drops, damage is advanced. Instead of asking how green is the field, I'm going to ask how uniformly green it is. Healthy fields are patchy with a standard deviation of 0.15, and stressed fields have uniform collapse with standard deviation of 0.01. Uniformity appears before the mean declines. And let's ask ourselves why this is new. Well, crop field surveys lag weeks, crop models require calibration, trend analysis can't predict anomalies, and mean NDVI, as we previously discussed, detects stress way too late. Tracking heterogeneity collapse provides 5+ months earlier warning. Healthy fields vary due to soil drainage and microclimate differences. Under drought, strong patches decline toward the mean towards synchronized failure. This occurs during stomatal closure and photosynthesis reduction, while mean NDVI reacts later at chlorophyll degradation. Our machine learning rigor was tested using various tests such as LOSO. Agricultural ML often suffers from spatial leakage via random splits. Instead, we used leave one state out cross-validation using 9 corn belt states. We train on 8 states and test on an unseen ninth. Our dataset was 116 county years with 12 stress events with less than negative 15% yield anomaly. Our data sources included Landsat 8.9 with 30-meter resolution, NDVI, EVI, NDWI, ERA5 weather, USDA NAS yields, and 2011 to 2023 time series. Total, we extracted 66 spatial heterogeneity features, including percentiles of P05 to P95, standard deviation, IQR, and range, coefficient of variation, and early season trends from April to July. We reduced this to 20 principal components via PCA. For the model choice, our classifier chosen was L2 regularized logistic regression, and this was chosen for interpretability and control generalization and not black box overfitting. Our results were very promising. With LOSO performance, AUROC was 0.807, and our 95% confidence interval was 0.67 to 0.92, and our permutation test had a p value less than 0.02. And notice our confidence interval excludes 0.5, showing that our results were statistically significant and not due to chance. Across 9 global regions, we had an AUROC of 0.955, and again evaluated with geographic separation. Together, we detected major disasters such as the 2012 US drought, as we mentioned, 2021 Canadian heat dome, and the 2022 European drought, all with an above 85%. Here was our lead time advantage. We had a lead time advantage of 5.1 months, and our earliest was for the 2012 US drought with 7.2 months. Traditional NDVI monitoring, whereas, only has 1 to 2 months of extra warning time, and we gain extra 3 to 5 months of actionable warning. We can see that we have a lot of feature importances as well. Our model aligns with the hypothesis. PC1 heterogeneity composite was an additional 0.82, PC3 low percentiles was negative 0.61, and PC5 the water index was negative 0.43. We show that higher variability equals lower stress risk. 5 months from our research enables that farmers can see their irrigation and input adjustments, insurers can see early loss modeling, and policymakers can start dealing with food security planning earlier, much before failure becomes irreversible. However, we did have some limitations. Due to the recent usage of satellite data, we only got 116 county years. We could only use a single crop, which was corn, and we had a very Midwestern focus towards the Corn Belt states. Future, we want to incorporate Sentinel-2 integration, multi-crop expansion, and real-time operational system. The big picture is that climate volatility is increasing. By analyzing spatial patterns instead of averages, we unlock months of earlier warning, a small conceptual shift with large agricultural implications. Thank you, and this is my genius submission.